So here are a few questions. How do you build a functional interface for process management? So as you see in this slide, you basically will have multiple processes based on the number of programs that you're running. Each instance of a program is a process basically. Every single thing that you're running is a process in essence. So how do you have a functional interface for process management so that you can manage the different memory areas, the registers, the I/O of the processes, and so on, and also the CPU time, of course. Should a program or a process be allowed to create an instance of another program, or stop it, or communicate directly with it? Let me give you an example. When you are actually running in Google Chrome, for example, you can start a new tab, and the new tab is for a computer basically a new process because you're going to do something completely different. Maybe one of your tabs is just static HTML, and the other tab you have some active some client um, some client application, or even some like JavaScript or something running in your other browser. So in essence, these are two different processes. Then how should the program communicate with, for example, your screen, your monitor? How should it communicate with your hard disk, and so on? And this is basically what this course is mostly about. And there is no silver bullet to do this. Each operating system has its own design. We're going to try to cover some generic design patterns for operating systems. Um, but yeah, you can basically come and say, oh, Mac OS doesn't work that way, or Windows does not work that way. Yes, sure, because it is a different operating system. I have to say most operating system books work with either Minix or Linux, because these are two open source operating systems, and they're basically, I mean, Linux is very widely used, and they are both Minix and Linux have basically inherited a lot of features from Unix, which is an old operating system. And there is no single correct method. You cannot say that, well, Linux is always better than Windows, or Windows is always better than Linux. Each one of them has its own trade-offs, have different design decisions that cater for different trade-offs, and basically you pick what you need. So the programming interface is basically what exposes your applications to the lower level components of your system, which are basically, if you look at this funnel sort of figure, sort of, you have at the very bottom the actual hardware, which is like your ARM processor, your PowerPC, which is a processor type. You have your x86, which is most Intel processors and AMD processors. You have the Ethernet card, the NIC basically, which is your physical card and physical connection to the internet. You have LCD screens, you have graphic accelerators like GPUs and stuff. So you have all this hardware. On top of that, you have a portable operating system kernel. And the portable operating system kernel is typically divided into even multiple layers. So you have something that's called HAL, the hardware abstraction layer. It's not clear in this graph. Well, it's not even in this figure. And the HAL basically is the part of the operating system that directly deals with the hardware. And this is the part that you have to change, or that you have to typically make changes to, in order for your operating system to run on different platforms. So if you're going to run Linux on an AMD machine versus if you're going to run Linux on, for example, your cell phone, these are two different platforms. And you would typically change the HAL layer. Then on top of the HAL layer, the hardware abstraction layer, there is another level for the kernel, which is mostly the things such as the scheduler. It's basically the controls, and these controls typically do not change between different platforms. And then on top of that, you have what we call the system call interface, and the system call interface is what is exposed to the programmer to use, or to the programming languages rather than the programmer to use, in order to access the different hardware capabilities. So if you're basically going to do rendering on a GPU, for example, you need to be able to instruct the GPU to do rendering. If you're going to open a file on the on your disk or on your USB stick, you basically need to actually touch the physical hardware to open this file. So basically, the system call interface is what is provided by the operating system for the different programs, or for the different typically languages, programming languages to use. And you typically also have a portable OS library on top of that. I mean, this is a thin layer over the system calls, but it's, yeah, uh, it is basically the kind of thing that you would find when you're running on Java. For example, you have the JVM that, so if you're writing Java code and you're compiling Java code, you typically write Java code without even thinking about what is the underlying operating system. You just write it. I mean, there are very few things that wouldn't work on Linux if you basically program with Java on Windows. At least it used to be like that. This used to be basically the idea of having Java. And the way it would do it was basically it would add a portable operating system library that would basically that is like the Java virtual machine, for example, would manage that, so that when you change from an operating system to the other, you will actually have the same, almost all the same methods and functions. Well, methods, because it's Java. You'll have all the same methods, all the same libraries running for both platforms. And then you have on top of that whatever you're going to run as a programming language, as a program, which is basically your web servers, your compilers, your SVN, source code control, your word processing, etc., etc. So to build this interface, you need four main characteristics. The first one is flexibility. You need one stable interface that allows for portability across and backward compatibility between different systems, between different hardware, and so on. If you have been programming in C and C++ for Windows and tried to reuse the same program on Linux, this is a pain. I mean, this is real pain, for example, because the libraries are not the same, the calls are not the same, and this is basically because you're missing the portable OS library. And the system calls are different between Linux and Windows, so it's not that flexible. So yeah, but at least if you're programming for Linux, then all your C program or all your C++ programs that you program for Linux will typically run on any other Linux system, unless it's wildly different. People try to basically make the system call interface also sufficient for all the different applications that you can ever run on top of it, so that there is no single application that requires a new system call, for example. And then you need it to be safe. You need the programming interface to be safe. And by safe, I mean that if you look at this figure, you have multiple applications running on top of your, if you basically even do not have the portable OS library and you have just the system call interface, you'll have all of these applications basically running on the same hardware, and all of them trying to access files, all of them trying to access memory, and so on. So you want your programming interface to not allow for illegal access to areas in the memory. For example, if the web server is trying to access an area of the memory that belongs to the databases, for example, you should stop it. You should basically even kill the web server, because you should be safe. So the programming interface should be safe. It should be reliable. So part of it, the safety part, is basically making sure that no one from on top of you misuses the programming interface, basically the applications. Reliable is basically you make sure that there are no bugs in your code, because if there are any bugs in your code, that means that you can mess up the whole user and kernel data and result in even losing the safety property, because, well, some people can exploit this bug, and this bug can even kill the whole computer, or the computer or the program, even without anyone exploiting it. So Linux has a philosophy that is basically, and even more severely, microkernels, we'll talk about them later in this lecture, that less work is actually less mistakes. So if you have 100,000 lines of code versus if you have 100 million lines of code, well, there is an order of magnitude possible number of bugs and mistakes that you're going to make. And mistakes and bugs actually grow exponentially, because the more code you write, the more interactions between the different components there will be, and the more you're likely to make errors and bugs in your code. So less work, less mistakes, so you try to keep your programming interface minimal. And you want your programming interface to be performant. And by performance, it means that it should be very thin layer. It shouldn't really use a lot of CPU time, a lot of of memory to just run a single call of these. So suppose that you're opening a file, and opening a file takes 15 minutes. That is something that would not be acceptable. But you might be thinking that, well, I'm opening the file, but I'm using the latest and greatest encryption method, and I'm using the most the best privacy control methods, and so these you can add on top, because some users might need this, and then they will be willing to wait for 15 minutes to open a file. But me, as a user who just wants to write something or make a presentation, I wouldn't tolerate such long delays. Even if you tell me that this is more safe and more reliable, I just want it to be also performant. So process management. It allows the program to create and manage their own processes. This is part of what the kernel allows the program to do. And this includes, for example, starting new tabs in your web browser, adding new users to your database, adding new tables to your database, and so on. You do not need to recompile the kernel code every time you install a new app on your mobile phone. Also, this is part of the process management, because although you're basically going to, even if that new app will measure your power consumption, will measure your signal strength, and will make calls on behalf of you, that wouldn't need you to recompile your kernel code, because, well, the programming interface is flexible, such that even when a new app is installed, the kernel doesn't need to change. The new app will just use the current and the programming interface that is already provided by the system. So let us talk about the way that Windows does process management, and we will talk about the syscall to create a process. So you want to create a new process, you want to start a new program. There is a Windows syscall that does just that, which is create process. Okay, and create process is basically a way for a process that is already not running to create a new process inside. So if we're talking about here tabs in your web browser, so when you start a new tab on your Edge, your Microsoft Edge used to be Microsoft Explorer, when you start a new tab in your Chrome, you're actually calling the create process syscall. So the process creator is for the parent process, while the created process is the child. So when you create a new process, so when you first start Chrome or Edge, you have a parent process, and this parent process is basically the actual program. And then each tab you create is basically a child process to this parent process. You can kill separate tabs, but you can also kill the whole Edge or the whole Chrome process. If you look at Chrome, for example, each tab will have like the X for closing this tab, but you will have also for the whole window a larger X that closes the whole parent process, which is in that case your Chrome. While this is very simple in theory, it's quite complex in practice. This is the actual interface. So create process, and it takes a pointer to the program that creates and takes some arguments. So the kernel needs to do the following on a syscall, on the create process syscall. Okay, it needs to create and initialize the process control block PCB in the kernel. This is the process control block is basically in the kernel, there is a data structure which has for each running process all the information that is related to this process. So hence it's called the process control block. And by all the information needed for this process, I mean, for example, its memory bounds, its PC, its program counter, what files it owns, what files it can open, what files it can modify, and so on. So the PCB is basically a pair program, a pair process data structure that basically tells the kernel, okay, for this process is allowed to do these things, and this is its current state. Okay. It also once you have the PCB, you initialize the PCB in the kernel. You create and initialize a new address space. So you basically take a chunk of memory, cut a chunk of memory, and allocate it to this new process, to this child process that you're starting. And then you need to update the process control block because now you have a new address space for this, right? And then you need to load the program into the address space, and the program prog, I mean, this is basically the pointer we have, the pointer we have over here, the char pointer we have over here. So you need to load the program into the address space. So now you have the instructions and everything that is related to this program into the address space. You need to copy the arguments into the memory or in the address space. So you have passed some arguments for this program. Now you need to put it in the address space. You need to initialize the hardware context to start execution start. So you basically need to jump into the init function. We're covering that in more details later, but you need basically to tell the hardware or to tell the PC, the program counter, that this is the line at which you're going to start. You need to inform the scheduler that the new process is ready to run, and other things that you need to do. You need to control the I/O. You need to, so what files this new child is allowed to touch and to change. You need to control the privileges. Can this child process create new children, for example? So you can have grandchildren for the parent process. You need to control the scheduling. So for example, you might allow your Chrome to do some scheduling. It doesn't have to be that only the operating system is doing the scheduling. So suppose that you have 10 Chrome tabs open. You might allow Chrome to basically allocate, and now Chrome is running. So which tab should it allocate the CPU time to? So you might allow Chrome to just do that, to just choose which tab to allocate now CPU time to. And you want to make sure that the process is benign. So the syscall should be safe and not expose the kernel. So you want to make sure that this new Chrome tab that you're starting is not going to overtake your whole computer and lock you out of your computer and not allow you to use your computer. So create process in reality takes 10 parameters as input, and this is a lot to do. Unix, on the other hand, and Linux has a much more elegant way of creating processes. And it has a philosophy that the Unix process API, I mean, Windows has like tons of these. The create process is just one of them. That Windows is enormous. That the Windows syscall structure is enormously large, and it was not even open source, so you couldn't really know what the different syscalls were unless you got these very expensive books. So it was not something that you could get easily, and people have tried to reverse engineer it. And I think last time we had a couple of links that pointed you to a list of Windows Windows API, and to the Windows API, and to the Linux API, to the syscalls. Unix has a different philosophy, and it's basically the Unix process API should do the following. It should be able to create a new process, destroy a new process, wait for a new process to finish, have some miscellaneous controls, and have a way to check the status of the process. So create a process. This is like an operating system must include some method to create a new processes. Just like Windows create process, Linux and Unix-like systems need a way to be able to create a process, a new process, basically a new Chrome tab. You need to be able to destroy it. Since you have been able to create it, you want to also destroy it when you need to. And of course, many processes will run and just exit by themselves when complete, but you also want to be able to kill them whenever you want to kill them. Okay, so like basically exiting my Chrome. You want to be able to wait. Sometimes you basically want to wait for a page to load, for example, on Chrome, or you want to, before you do something else, you might build a program such that before you do anything, you want to make sure that that the child is now running and has done some progress into computations and so on. You need some miscellaneous controls other than killing or waiting for a process. So for example, you sometimes want to suspend the process, basically make it sleep. You want to be able to resume it. So you might want, for example, to run periodic tasks on your computer. So at 12 p.m. every day, you want to do a backup, right? So you want to be able to make your backup script to sleep until 12 p.m. every day, and on 12 p.m. it resumes, it does the backup, and then it goes to sleep again. And you should be able to check the status. Okay, so what is it running? Is it doing well? How long has it run for? And so on. So process creation happens like this in Linux. The first thing the operating system must do is to load the code and any static data into memory, the address space of the process. So you basically have the code running on the code basically residing on disk. So you have a stored program on your disk, like all your applications are. And when you start create the process, when you start it, you want to basically have stack, and you want to have a memory address space, chunk of memory for this process basically, and you want to just be able to load the code into the memory. And then early operating systems perform this task eagerly, basically by pushing the whole program. So if you're running a game, for example, the early operating systems would just take the full game, load it into memory. Right now, you never do that. So, for example, if you're playing a game, the game will load bits by bits into the memory, basically the parts that you need, because every game is just like, you're in certain level or into a certain level or a certain environment, so it doesn't need to load the whole game, but it just needs to load the current level that it's running on. A modern operating system does this lazily by basically loading pieces of code and data as they are needed. You want to allocate important memory regions once you have the code in place. You want to allocate the heap and the stack. The heap is basically for dynamically allocated data, and the stack is for storing local variables and function parameters and return values. So you want basically to be able to load this from again disk to memory. Heap is not really, it can be loaded basically as you as you run the program, you start filling in the heap. It doesn't have to be loaded from the hard disk. And then you initialize the process. The operating system will do some other initialization tasks, for example, making sure that the program has access to the right files, input, output, if it's going to use the GPU, if it's going to use the screen, and so on. For example, for each Linux or Unix process, you have by default 3 open file descriptors. The first one is standard input, the second one is standard output, and the third one is error. And these are basically 3 files. The first one, standard input, is typically your keyboard. And we'll talk a bit about the way that Linux views all your devices, all your I/O devices. But standard input is a file descriptor that is typically pointing towards your keyboard. Standard output is basically a file descriptor that is typically pointing towards your screen, your monitor. And error, which is a file that where basically if there are errors will be logged into that file. Okay, so right now, as the process is ready, now everything is set for the process. You can start running, and running typically starts from a special function called main, which is basically when you program in any language almost, you need to specify a main language, a main function or a main method. Yes, and some compilers are intelligent enough to understand that if you have not specified a main function or a main method, it will just start from the beginning till the end of the program. But for example, in Java, you would specify main. In Python, if you want, for example, to start at a different place than basically going sequential, or if you start having multiple functions in your program or multiple classes, then you need to specify also a main method. So this is used by the operating system to basically locate where it should start running the application, and it jumps to main basically. Once you're ready, once you have all the data on memory, you jump to main. And you transfer control of the CPU to the newly created process, and thus the program begins its execution if it has been allocated time on the CPU by the scheduler. So these are the processor states. Basically, you start when you have been just initialized, you're ready. Okay, so you have just loaded everything into memory and you're in that state. You have pointed to main. That doesn't mean that you can start running right away. You start at the ready state, and once there is CPU time for you, once the operating system decides that it's time to run to run this process now, it will schedule the process onto and the process will be running. Now the status of the process is running. The process can either continue running until it finishes, until it completes. This is one way, or it might be descheduled by the operating system. So suppose that this is a very long process, it's taking way too much time. Now I need to switch to some other processes, some other programs that are running in parallel. So suppose that you have Chrome running with Skype, for example. You do not want, and you have a long Skype call, you do not want Skype to overtake the whole process time, and then you will not be able to browse the internet while you're on the video call. So you would want to share the CPU resources between the two applications. So you want basically to deschedule the process and get it back to ready state, run the other process for a while, and then switch. A process while running can basically go into a phase where it needs to read something from I/O. So it's either waiting for user input from the keyboard, or it's waiting for some file reads from the disk, or it's waiting for something to fetch from memory. So now it no longer can run because it needs this data. It needs to go and fetch the data from memory or from disk or from your keyboard, or it's sending data to your screen, to your monitor, and it needs to wait until that data is presented before doing anything else. So the process in that case would run from would move from the running state to the blocked state. Now it's blocked; it cannot do anything until you basically do some input from your keyboard. So when it's blocked, another process can start running, and the process that is blocked will remain in the blocked state until the I/O is done, until the input/output is done. You have basically typed something, you have done the given the process the input, so now the process can move from the blocked state to the ready state. It can never move from blocked to running. It will always move from blocked to ready, and then it has to wait in the queue until there's some time for it to run. So I just basically covered all this. So if you look at process states, CPU only, so you have process 0 and process 1. And this is one mode of operation where you have process 0 arrives first and it starts running, and it's running, and it's never stopped. While process 0 is running, cannot really use the CPU if we have a single core CPU, so it needs to wait. So it waits in the ready state, so ready until basically the process 0 is done running. So now no more process 0 at time unit 5, and now process 1 can start running and it runs to completion. This is one way. Now if you add I/O, process 0 started running and it ran for 3 time units, but then it started needing some I/O. It needs user input, so it gets blocked on basically the 4th time unit, and process 1 can start running. And process 4 remains blocked for 3 time units until it gets its I/O is done. It has fetched data from memory or from disk or has input from you on the keyboard, and then it moves to the ready state. Process 1 continues running. It doesn't need any I/O, so it continues running until it's basically done, and it moves. It's done. So when it's done, it's basically it goes to a finished state, sort of. And until process 1 is done running, process 0 is now ready, and once process 1 is done, process 0 can start running until it's done. There are kernel data structures, and these are special data structures in the kernel itself, in the operating system. You might know them already from you will know most of them basically from your algorithms and data structures class. So you'll know that what a linked list is, what a heap is, what stack is, but these data structures are used inside the kernel. There are some very special data structures inside the kernel that have actually evolved from inside the kernel and now are used in other programs. But there are many data structures in the kernel. One of them is the process control block that I actually touched upon a while ago, which is a C structure that contains information about each process, and the other one is the process list, which keeps track of all processes. It basically is a linked list of all the PCBs. It's a double linked list for all the PCBs basically.